and the laser. Okay.
Okay, so we continue talking about the DUNE project, and now we have Ernesto Kemp, who is going to tell us about neutrino oscillation and supernova neutrinos at DUNE.
Okay, thank you. So it's nice. I'm feeling like a referee of soccer using this stuff here. So thank you for the organizers for this opportunity to talk about neutrino oscillations and supernova neutrinos detection in the DUNE experiment. So this is the outline of my talk. I will describe you some interesting facts about neutrinos, and then just one slide about the DUNE concept, because Ettore did a very good job describing the detector in his talk. And then I will move to neutrino oscillations, just the baseline of the phenomenon, and the DUNE capabilities to study the neutrino oscillation physics. Then I will do the same for the supernova neutrinos, and then I'll draw some conclusions. So why neutrinos? First of all, they are super abundant. They are just behind the photons, and if you change the classification and analyzing by the fermion point of view, they are the most abundant particles. So neutrinos have been produced in the universe since the early times of the cosmological times, in each weak process that have been occurred, and so inside stars and in very extreme astrophysical environments. So they are numerous and they are everywhere. Second interesting fact is that neutrinos are almost massless. They are the tiniest particles that have mass that we know. And this is the mixing patterns of neutrinos and quarks are very different, and also the mass patterns. So there are some interesting proposals to explain that, and Esteban already mentioned about that, the seesaw mechanism, that it's very useful because it has the bonus to explain the mass of the particles, and also it's related to leptogenesis that can explain the asymmetry of matter and antimatter in the universe, and also can relate the sectors, can connect the lepton and the quark sectors. Another question is the matter-antimatter imbalance in the universe that we are observing. Nowadays, we observe less than a proportion that is less than 10 to the minus 7 in fraction of antimatter related to the matter in the universe. But in principle, during the early times, in a certain point of the universe evolution, neutrinos could be the responsible particles to start to trigger this kind of mechanism that has provoked the disimbalance between matter and antimatter. And for the last, we have the supernova explosions, because neutrinos seems to play a key role in the supernova of type 2 that is related to stellar collapses. And in this kind of explosion, we have a large amount of mass ejection to the cosmos, in which the heavy elements are ejected to the cosmos, and these heavy elements afterwards are used to form planets and stars and so forth and so on, and even complex structures just like live beings or life itself. So it's likely that the iron that we have in our blood cells once was inside a stellar core. So, okay, this is the DUNE mission and concept. I will not get into details. I will not go into details about the detector, because Ettore has already explained about that. But these are the mission of the experiment in very few lines. So what's the experiment? It's being built to try to explain and try to have an answer about the imbalance between matter and antimatter, and also to look for these underlying symmetries or hidden symmetries connecting probably the leptonic and the quark sector, and also if there is or not a grand unified theory, or a scale in which all the interactions can be put in the same grounds, and also to explain the explosion of supernova, and if there is a new physics or not behind the neutrino bursts. So these are the key elements of the detector that was explained by Ettore. So let's move now for the neutrino oscillation physics in just 3 slides. First of all, neutrino oscillations rise from neutrino mixing. This is a result that the flavor eigenstates that is related to the interaction process don't coincide with the mass eigenstates that is related to the propagation. So the Hamiltonian of the propagation have some eigenstates that are the mass, and the Hamiltonian of the interaction is related to the flavor eigenstates, and we can link each other through linear combinations given by the PMNS matrix. And this matrix can be decomposed, you can factorize it in 3 successive rotations that can be interpreted as 3 successive rotations. And each one of the matrix, we can isolate functions of the mixing angles in each one of the blocks. And just to give you a more physical sense about this abstract view of mixing angles, it's interesting to note that the meaning of the tangent square of theta 1, 2 is the fraction of nu e in nu 2 over the fraction of nu e in nu 1. And the tangent square of theta 2, 3 is the ratio of nu mu to nu tau in the nu 3 eigenstate. And the sinus square of theta 1, 3 is the fraction of nu e in nu 3. And it's interesting to note that we have an overall phase factor here that is related to the CP violation. And if you have a non-zero value of the delta CP, it means that neutrinos and neutrinos should oscillate in different way. So what do we know? We know a lot because we learned it. There is a lots of experimental and theoretical effort here in the last 20 years. And so we know that the order of some elements in the PMNS matrix. We also know that the difference in the square difference of mass eigenstates in the solar scale has this value, and for the atmospheric scale, as Esteban showed us in this morning, we have only the modulus of this value, and we should know the sign of this to explain some properties of the neutrino interactions. And you know a lot about the mixing angles, but we have to make, now we are in the stage to make precision measurements. And DUNE, apart from the things that I will discuss in the next slides, there are CP violation measurements and neutrino oscillations. One of the missions is to make precise measurements of these parameters, doing simultaneous fits between neutrinos and antineutrinos results, and where it's possible to get a more precise values of the mixing angles. And another question, as you can see, is related about the value of the sinus square of theta 2, 3 that we don't know. So again, this was discussed this morning, the mass hierarchy and splitting, that is also called as neutrino mass spectroscopy. So we should know, we have to understand if we have a normal hierarchy or inverted hierarchy, that it's simple means that we don't know if the nu 3 has a bigger mass than the different scale of the solar split, or it's inverted in the case that nu 3 is lighter than the nu 1 and nu 2. And also the sign of this mass splitting, we don't know that it can affect the oscillation probabilities, as I will show you in a few slides. So another interesting question, it's the theta 2, 3 octant. So basically, it means that we don't know yet the dominant flavor in the nu 3 mass eigenstate. So if we have a maximum mixing, and if to 3 is exactly equal to 45 degrees, so it implies in some symmetry that will constrain the quark-lepton universality. So this is a very important measurement to be done, and to understand this, let's say, that it's not, there's no similarity between the lepton sector and the quark sector concerning mass patterns and mixings. And also, as you can see, and I discussed it in the second slide, or third, I don't remember, DUNE is looking for the CP violation that can be observed in neutrino oscillations at low energies that can be translated or can be linked to try to explain the baryon asymmetry at good scales, and then explain the imbalance between matter and antimatter that we observe nowadays. So, one interesting thing concerning the CP violation is that the standard model in the weak interactions allow the CP violation, but they are CPT invariant. So under CPT transformation, neutrino and anti-neutrino oscillations are equivalent. And this was tested by the Minus collaboration, and there was no evidence for CPT violation. So this is very important, because this means that asymmetries in neutrino versus anti-neutrino oscillations just came from CP violation. And this can only be assessed by appearance experiments. This means that, what is the difference between appearance and disappearance? Appearance is when you produce a certain flavor of neutrino and you detect another flavor. And disappearance is when you produce sometime, let's say nu mu, and then after the neutrino propagation, you observe a number, a flux that is smaller than the original flux. So this is the called disappearance mode for neutrinos detection. But the CP violation can only be assessed through appearance experiments. And here are the probability of to observe the oscillations from one flavor to another, and it can be decomposed in 4 terms. And this one is interesting for us because this is the CP violating term. And this is because you change sign of this term here in this sum when you go from neutrinos to anti-neutrinos. You change for the minus to plus signal. And this term here is an even term that conserves the signal even if you have particles or antiparticles. So it doesn't matter for the probabilities. And this, this is the term that can change the oscillation probabilities. And here are what these probabilities in the appearance in particles and antiparticles looks like in DUNE, in the DUNE case. So DUNE will cover this range here of energy between 1 and 10 GeV, as actually show you the spectrum of the neutrinos that I produced at the Fermilab beam. So the expectation is to measure one full oscillation length at the far detector to observe these structures here. And so this is the DUNE sensitivity concerning the disappearance spectra. So it's not related to CP violation measurement. And here you can see that we expected just a big hump between, in this energy range, between 1 and 8 GeV at the production site, but the oscillation probability will modulate the spectrum showing these 2 peaks here. So this is the case for neutrinos, this is the case for anti-neutrinos, and as you can see, the shape are very similar, but the counting rate, the flux is very different. This is in the case of normal hierarchy for both particle and antiparticle mode. So it's possible by the counting rate to understand what is the disappearance spectra, and then related this to different values of the oscillation parameters. So here is the spectra that are related to CP violation measurement. So this is the appearance spectra, and here we have for normal ordering, and here we have for inverted ordering of the neutrino mass scales. And again, As you can see, the shape of the spectrum in this case is very different from the previous one. And here we have the solid line that it's a simulation and reconstruction by the official DUNE Monte Carlo simulation reconstruction chain. And the solid line is for a value of delta CP equal to 0. And these gray lines is the other extreme case, when you have delta CP equals to minus pi over 2 and plus pi over 2. That is the extreme case for that can affect the shape of the spectrum and the counting rate as well. So here you can see that it's, again, the shape is similar, but the counting rate is very different in these two cases. And here are the same, but for anti-neutrino mode. So in each case, in each of the two cases, is expected the minimal expectation, the minimal plan for the data taken in DUNE is 3.5 years in each mode. So, of course, there are plans for 10 years, 15 years, but this is the minimum that it's being considered for to take data in both modes. So again, here we can see that the shape cannot, let's say, give you some very clear information, but the rates in the two modes, and in the case of normal and inverted hierarchy, it's totally different. So let's briefly describe these results for the previous plot in terms of the sensitivity to identify the mass hierarchy. So here is the delta chi-square. It's simply you take the chi-square of the fittings in case of the normal hierarchy, and you subtract for the inverted hierarchy. And this is the delta chi-square. That is the matrix for to identify if you have normal or inverted hierarchy. And this is the significance in terms of years, of the calendar years, when you start to make the data taking. So it's possible to see that after 2 or 3 years, this red band is for delta CP equals to minus pi over 2. And in the blue band, it's 100% of delta CP possible values. So as you can see, the significance of 5 sigma can be achieved after 2 or 3 years of data taking. And here we have two plots in the x-axis. We have all the possible values of the delta CP angle. And here are the significance in which we can identify the hierarchy of neutrinos. So the purple band, it's for 7 years of data taking, and the orange, yellow, I don't know, is for 10 years of data taking. And so as you can see, the sensitivity for DUNE after a long mission is very, very high to identify the mass hierarchy. So let's move for the CP violation. And in CP violation, here we have the same kind of plot. That is the significance that can be achieved after as far as the time goes on. And so these values now are, here we have the minus pi over 2 value for delta CP, that is an extreme value, so you can reach higher sensitivities very soon. And then this blue, the light blue, is for 50% of the possible delta CP values, and this more dark blue, it's for 75% of the possible delta CP values. And here are the sensitivities again for the delta CP, the same plots that I showed before for the order of the mass ordering of neutrinos, but now it's for the CP violation. Here we have the possible values of the CP violation and the significance in terms of the delta chi-square. And again, the purple band is for 7 years of data taking, and the yellow band for 10 years of data taking. So 5 sigma sensitivity is an ultimate goal for a definitive discovery for DUNE, and it requires very strong work, and mainly based on the capabilities of the near detector. because the near detector can constrain let's say, in a very hard way, the systematics related to flux cross-sections and other issues of the interactions and the backgrounds at the near site, and then it can constrain a lot the systematics of the oscillated flux that will be measured at the far detector. And to finish about the DUNE sensitivities about in the oscillation physics, this is a very nice plot about the octant and the value of sinus square of theta 23, and this means the maximum mixing, and this is the sensitive, and as you can see, for non-maximum mixing, we have a larger significance that can be achieved by the DUNE data. And, but one interesting fact is here. So in those yellow island this is a simulation using the new fit, that is the group that has been shown for many different people this morning. And this yellow island, this is the value, is the most probable value find with a simultaneous fit of each experiment that is available for neutrino oscillations. This is the value for the new fit for theta 23, sinus square of theta 23, and it's related to this CP value. The value of the CP angle is here. But it's interesting to see that when you consider 7 years of data taking, that is the purple lines, as far as time goes on, you remove, for instance, this kind of degeneracy, and you keep the island just around the central values. So after 10 years or 15 years, you can remove these ambiguities, these degeneracies, and you can constrain much, much more the possible values of the angle and the relationship with the delta CP violation. So, too much for oscillations. Let's move for supernova neutrinos detection. And so this is what we believe that happens inside a massive star. So there is a sequential fuel burning, and in the main sequence of the evolution of stars that lies in the main sequence of the Hertzsprung-Russell diagram, successively burns different, you form heavier and heavier elements inside the core. So you start to fuse hydrogen into helium, oops. And then you burn helium to form carbon, and then oxygen, silicon, and then iron, and you cannot go further away because iron is the nucleus that have the most binding energy. So a process that to fuse for another heavier element will be energy endothermic, and then it's not favorable so it will absorb energy, and it's not possible to do that. So this is onion-like structure of the core of the star. This is pretty much in scale. When you have this red bubble is the hydrogen envelope, and in a very small core size, you have the onion structure with heavier and heavier elements. And more massive the star is, you can burn heavier elements, and then depending on the mass of the star, at the end you have helium, oxygen, silicon, or iron in the center of the star. But for stars with mass bigger than 8 solar masses, we can have this phenomenon here, that supernova explosion. Here are 15 years of studies of supernova in just one slide. So within a massive evolved star, first of all, we'll have the onion-layered shells that I just described for you, and the elements undergo fusion, forming an iron core. This is for stars with mass greater than, bigger than 8 solar masses. So what happens inside this iron core? When this iron core, you start to burn silicon, and this silicon increases the size of the iron core, and when the iron core it's bigger, Then the Chandrasekhar mass. What is the meaning of the Chandrasekhar mass? The Chandrasekhar mass is the limit of the mass of the iron core that can support the pull, the gravitational pull, and the particles that are responsible for that is a degenerate gas of electrons, okay? So they are relativistic, since then they are very energetic, and so the pressure is much bigger than a simple gas of electrons, and they are responsible to support the stellar structure against the gravitational pull. So since you are above the Chandrasekhar mass, the inner part of the core start to compress. So gravitation wins over the pressure of the electrons, and then you start to squeeze the electrons into the protons, and you start to form neutrons. This is why we have a neutron star as a possible end, if not a black hole, depends on the mass of the progenitor, as an end of this process. So what happens in this C square? So the inner part of the core is compressed into neutrons that I just explained to you, but now there are interesting physics process here. That is, you have a nucleus of the star that is practically one big nuclei, okay? So it's a kind of chemistry, a kind of chemical nuclei that it's made of 10 to the 50 atoms, nuclei, different nucleons. And then here, now, what is the degenerate state of matter are the nucleons and not the electrons. And then what we have is a phase transition, and the gravitation cannot longer anymore to compress the nucleus. And then it happens something like when you squeeze a spring, and then you open your hand, and the spring just release this potential energy, and this is what happens with the core. So the matter that was falling down in direction towards the nucleus of the star, the core of the star, now invert the direction of the movement, and you have a kind of shock wave outwards that tries to pulling out the matter that is falling down over the stellar core. But this shock wave starts to lose its energy. Meanwhile, it traverses the external layers of the star due to energy dissipation. And then here, there is the possibility that the neutrinos plays an important role in supernova explosion. That is because behind this stalled shock, the neutrinosphere starts to emit free neutrinos. And the flux of neutrinos is big enough to make some energy deposition in where the shock stopped to pull out the matter, and then the shock is revigorated by the energy deposition of the neutrinos, and then you have finally the explosion with the mass ejection towards the cosmos, and you have the supernova explosion. So this is related this is a scheme for the type 2 supernovae that it's linked to stellar gravitational collapses. So let's connect all the history that I told for you in terms of neutrino emission. So we have the neutronization burst that it happens just after when you start to crunch the core and squeeze the electrons inside the protons, and you have the proton neutron star that is being to be formed. You have a huge emission of nu E, and these are the luminosities in 3 different phases. This is for the gravitational collapse, and when the shock starts to propagate outside. So you have the accretion phase, in which the matter still falls down inside the core, and the shock wave is still fighting against the matter that is falling down the stellar core. And then after, as I said to you, after the removal of when ejected material is launched outside the star, we have the cooling phase of the neutron star, the recent formed neutron star, And we have a very long cooling phase that it's achieved by the emission of neutrinos in 3 different flavors. So here NEX stands for all non-electronic flavors and their antiparticles. So here are the plots for the luminosities and in the neutronization burst, the accretion phase, and then we have exponential falling down of the luminosity at the cooling phase. So at the terrestrial detectors, we expected to have the largest part of the events in this phase here. But these are the average energy for the 3 different types of neutrinos that you can see that it's always around somewhat between 10 and 16, 15 MeV. And one interesting feature is here, that we have lots of electronic neutrinos emitted during the neutronization burst. Okay, so just to give you an appetite of how the spectrum of neutrinos should be, and in many different computational and numerical simulations of supernova explosion, this is a very famous shape of spectrum that fits very well different models, and it's simple based on 2 parameters, that it's the average energy of the emitted neutrinos, and alpha, that it's parameter that is related, it's called the pinching parameter, that can be translated in the deviation from a pure thermal spectrum. So you can have a more narrow spectrum, which means that you have larger values of alpha, and for small values of alpha, you have a more width in the spectrum. Okay, oops. So for DUNE will be plenty of liquid argon, and then cross-sections, it's a very important issue for us. And here you can see a plot of the cross-sections in terms of the neutrino energy, and we have different channels, elastic scattering over electrons, charge current interactions, that means the absorption of neutrinos by the argon nuclei, producing potassium or chlorine with the emission of the respective lepton, electron, or positron. And then there are some possibilities, but there are theoretical uncertainties, and we don't know, as a matter of fact, very precise way in which the neutral current interactions or scattering of neutrinos of each one of the flavor, of any flavor with the argon nuclei, that can produce an argon excited state and can decay emitting photons. And this is a very nice interaction that if we can observe, as you can see, the possibility to separate different channels by a classification of the associated photons that are emitted from potassium chloride and argon excitation, and can give us a better picture about the flavor of neutrinos that are interacting inside the detector in terms of the supernova emission. So here we have a plot with the expected rates for neutrinos from 10 kiloparsec here. No, this is in function of the distance. And we have the 2 scenarios. The green band is for just one modulo, a 10 keton of fiducial volume. And the red band is for the total DUNE, the complete detector. And of course, the uncertainties in this band are related to the collapse model, the neutrino oscillation models, and the distance. So in average, we expect 3,000 events by a collapse in the center of the galaxy that is around 10 kiloparsecs. And this is the time-integrated spectrum that we expected for 3 different interaction channels in DUNE. And just to remember you that the last supernova that was detected, we have seen 30 events in total, not probably less, 23 or I don't remember. If you consider other detectors, you reach 30 events. And this is the signal evolution, where you can see a large peak at the early stages of the supernova detection, mainly due to the detection of electronic neutrinos. So this is an important feature of the liquid argon detector. And when you use a kind of complementarity between water Cherenkov and scintillator detections, you can get a better picture of the supernova event. But DUNE has unique sensitivity to electron flavor component. And this, the DUNE has the capability to provide information on time, energy, and flavor structure. Another question that I was discussing with Pedro, and Pedro made a question for Esteban this morning, is about the oscillations in supernova cores. So we have collective effects that are lots of work being done in this direction, but none of them, there are no clear convergence for an answer about the collective effects in the core of supernova that takes place mainly in a radius that is smaller than 200 kilometers. Then we have a very well-established effects of the MSW oscillations and increase of and resonances in the supernova profile structure that was published in 2000. And even at that time, if we didn't know at that time the value of θ13, so this is a very nice article that I recommended to everyone that is interested in supernova neutrinos to read, and keep in mind that nowadays we know the value of the θ13. So then we have vacuum oscillations from the supernova to the Earth labs. But I would like to emphasize that there are, even if you don't know exactly what the collective effects can I have just 2 minutes more? Okay. So even if you don't know exactly, we don't have a clear picture about the collective effects, nevertheless, the different models predict this collective effect imprints in the final spectrum of supernova neutrinos. So as you can see, the dashed and the pointed lines are from unoscillated spectrum, and then in red and black, you see very different structures and very amazing structures that it's modifications on the energy spectrum due to collective effects and afterwards the MSW effects in the supernova core. So even if you don't know exactly, all the models can predict these strange structures in the spectrum, and to see that with the new generation of detectors, just like DUNE, there are some key requirements that energy resolution better than 10% and energy threshold above or around 5 MeV, that it's inside the proposal, the plan for DUNE. And so, this is a list of another physics topics, and that can be studied by DUNE. And DUNE, it's a complex of detectors and with many abilities that combine it, and with the large exposure and the place that is deeply underground, give you a rich physics program, including non-beam physics, not only the beam, the neutrinos from the beam. So there is possibility to study baryon number violation, that it's related to, for the GUT, the GUT, the grand unification theories of the physical interactions, the possibility to detect light-dark matter, sterile neutrinos, non-standard interactions via non-unitarity of the mixing matrix, and also who knows to measure that Minus was not able to do, CPT violation in neutrino oscillation. So conclusions. DUNE you have megawatt neutrino beam, 40 keton LARTPC deep underground, and flux and beam contamination uncertainty is under control due to a high capable near detector, as you could see in the Ether's talk. So the aim is to solve the neutrino mass hierarchy and the CP violation phase, the oscillation measurements. And we also have a high capability for neutrino physics and supernova astrophysics studies. And as I just mentioned to you, there's a rich non-beam physics topics. So future is promising. Thank you very much. And that's all.
Okay, questions?